Okay, so what? Tá ligado? So what we saw yesterday was, on the one hand, that we are trying to prove that lambda plus of nu k converges to lambda plus of nu, and we may assume that lambda minus of nu is strictly smaller than lambda plus. And we are also assuming that this does not happen, so that that this does not happen, and does not happen. And what we have seen was that as a consequence, there exists L in PR2, which is invariant expanding and an atom. An atom for the stationary measure, the limit stationary measure. So invariant means AX of L equals L for mu almost every X, and expanding means that the logarithm of the norm of AX V dot integrated with respect to X is positive for some n and C positive. So we had this consequence already from last week, and then the key to the proof of continuity is the following theorem. That's what I'm started already proving. That's the heart of the proof. It says, suppose that some point in PR2 is invariant and expanding. Let nu k be a sequence converging to nu, just a notation that we are, and eta k be eta k be a stationary measure for nu k. Nu k is stationary. For each k. Then the theorem says that this invariant point, invariant expanding point, V, is not an atom for any accumulation point eta of the sequence eta k. Okay, so this is really the heart of the proof. Eta is a measure that is obtained as limit of stationary measures for nearby probability distributions, V is an expanding point, then V cannot be an atom for eta. Okay? Expanding points cannot be seen as atoms by any measure. Well, there's an assumption. Suppose eta k is non-atomic for every k. Okay. So this is where we are in the proof, and now let me outline how we are going to proceed. Then I'm going to prove the theorem, and if you put this together with the theorem, so this proposition that we proved last week, the proposition plus the theorem lead to a contradiction if the new k are non-atomic. Okay, that's direct contradiction, because this is saying that there exists an invariant expanding point, which is an atom, and the theorem says no, that cannot exist. So the rest of the proof will be to deal with the case when the new k's are atomic. And that I will do at the end, but that's the easy case. Well, nothing is easy in life, but this is easier than the rest. Okay. It's not trivial, but it's not hard either. Okay. When I say here is stationary for every k, of course for every k large. This is something that are k for k large. And then the other case is when new k are atomic for, so I have to take the opposite, atomic for a sequence of values of k going to infinity. But in this game, I can always restrict to subsequences. So this is really about new k being non-atomic for every k or being atomic for every k. Okay, so I'm going to prove the theorem. What I was already started last time was in the direction of proving the theorem, and then at the end on Thursday, I will talk a little bit about the easy case. Okay, so we introduced this notion of coupling. Given eta in P here is just a compact metric space. I call coupling, a self-coupling is a measure C in P times P such that if you project into the first coordinate, you get eta. And if you project into the second coordinate, you also get eta. I will only deal with self-coupling. It's the coupling of a measure, self-coupling of eta. Is this. We define the delta energy as the integral 1 over the distance to the power delta integrated with respect to c. And we define the delta energy of eta as the infimum of the energies of the couplings, self-coupling. So I stated a few properties. I'm going to prove one, at least. The first property is that this map is lower semi-continuous. This is actually an exercise in the book, and I'm going to leave it as an exercise. This is almost the definition of an almost direct consequence of the definition of a weak star topology. This function is continuous. If you stay away from the diagonal, then you use the weak star topology, and then you have to put in the diagonal somehow, and that's where you lose continuity. You just keep lower CMAC continuity. So as a consequence, the infimum is always attained is attained. Okay. You always have self-couplings, but there's another exercise, which is that the infimum is attained among symmetric self-couplings. So I'm saying, first of all, that there exists some self-coupling whose energy is equal to the energy of eta. And I'm also saying that if you want, you can take that self-coupling to be symmetric. You can choose it to be symmetric. This is also an exercise. Easy. This one is easy. Okay, so let me prove something that is not so easy, which is that the energy is able to detect atoms. So if the energy of eta is finite, then every atom has mass at most one half of the total mass for every x. And the converse, if every point has mass strictly smaller than one half the total mass, then the energy is finite. Let's see. Yeah. The first statement is very easy. It goes like this. Suppose, this is by proving the converse. Suppose that there exists some point whose mass is more than one half. Okay? So suppose that there exists some point A here, such that the mass of A is bigger than 1/2 the total mass of eta. Okay. Now this is equal, since eta is the projection, this is equal to xi of A times P. This is A times P. Right? And this here is 1/2 of the total mass of xi, because I'm using the fact that xi is pi 1 star of eta. Projection preserves the mass. So what I get from the assumption, so suppose A is like this, then what this means is that this line has more than half the mass of xi. Okay. Now, I also have that xi is, eta is pi 1 of xi. I also have that eta is pi 2 of xi. Okay, so just for the same reason, I also have that this line, P times A, has mass, so C of P times A is bigger than 1/2 the total mass of C. Right? So this contains more than half of the total measure, and this also contains more than half of the total measure. Well, that implies that this point has positive mass. Okay? So this implies that xi of the set formed by AA is bigger than is positive. If this point had 0 mass, then you could say that these two sets are disjoint. Then the mass of their union would be the sum, and the sum is bigger than the total mass. Okay, so this implies that your coupling has an atom on the diagonal. Okay, and this is for every coupling C. For every coupling C. For every coupling. And as we observed last time, if there's an atom in the diagonal, then the energy of C is infinite. And since this is for every coupling, that implies that the energy of eta is infinite. Okay? So the first part is really very easy. It's just this argument. If you accumulate too much mass on one point, then that automatically forces existence of an atom on the diagonal for any coupling. So the infimum is infinite. So now the converse, this converse, and the idea of the proof is not very different from what I did yesterday with this measure that had 3 masses. It has to be a little bit more sophisticated, but essentially it's the same idea. So I'm going to suppose the assumption, suppose that every point has mass that is less than 1/2 for every x in P. Now this has a consequence, a little bit of topology. Then I can find number rho, small, positive, such that the measure of the ball of center x and radius rho is less. This is probably a little bit bigger than this, but this was smaller than a half of the total mass. So by continuity, I have this. By kind of continuity of the measure, if I take rho sufficiently small, the measure of this ball is smaller than the measure of its complements. By the way, this may be written, this is just the same thing as saying that the measure of x is less than the measure of the complement of x. Right? I'm saying that this remains true for a small ball around x. And by compactness, using the fact that P is compact, you can find this rho independent of x. Then, here's the idea of the proof. You take any point x. I'm going to pretend that x is here. Makes my life easier. Doesn't matter, of course. And I have a neighborhood, this neighborhood radius rho. And what I just wrote says that the measure here of this domain is bigger than the measure of this little ball. And similarly here. Okay? So I'm going to give names. I'm going to do one of these technical tricks. I'm going to write 2 here. Just replacing rho by rho over 2. So I have a somewhat bigger ball, twice as large. And this is the ball of radius 2 rho around x. And I have that the measure here of this domain is bigger than the measure of this little ball here. Okay? Now I'm going to take any coupling C, any self-coupling C of eta. I want to prove that if I choose another coupling in an appropriate way, I can find the new coupling with smaller energy than Xi. Xi is any coupling, could be just a product, the initial coupling, Xi0. It's any coupling. And I want to find another coupling with smaller energy. And as I explained last time, our problem with the energy is around the diagonal, because it's around the diagonal that this distance can be very small. So what I'm going to do, I'm going to take this initial coupling, and I'm going to displace parts of the coupling to other regions in such a way as to reduce and eventually cancel the mass of the coupling near the diagonal. So my goal will be to remove all the mass of Xi, 0, from this neighborhood. Okay? So we are going to construct a new coupling. A new coupling, C1. And here is C1. Here is who I want to take as C1. So I'm going to give names to this domain here is B. B is the ball of radius rho. I'm going to call this C, the ball of radius 2 rho, and I'm going to call D the complement. So the complement of the ball of radius 2 rho around X. Okay? So here is my construction of C1. C1 is just C0, but I want to remove all the mass from this domain here because it's near the diagonal. Of course, there are other points near the diagonal, but let's go by steps. Okay, the first step is to remove the mass from here. So what I do is that I subtract C0 restricted to B times B. If you want, it's the same thing as taking the restriction of C to the complement. Okay, this is just this. Up to this point, this is the same as C0 restricted to the complement of B times B. Now, there is a problem when I do this. Remember that a coupling has to project to eta. But I removed this part here, so it doesn't quite project to eta. And I have to compensate for that. By the way, I'm going to take any symmetric. I'm going to do the whole construction in the space of symmetric couplings. So I have to compensate for this, for the measure that I removed from here. And I'm going to do that as follows. I'm going to put here exactly what it takes to compensate for this, so that the projection remains nice. Okay? I also have to worry about the other projection, but let's go by steps. So, let zeta be any coupling of eta restricted to B and by this is D here, this is C, and this is B, by what? By the projection of C restricted to D times D. So I take the measure here in this big pink square. I project it, I get something here, and so here I'm putting the coupling of eta restricted to this by that projection. No, this is not correct as I wrote it, because you remember that I can only couple measures that so here I'm going to write plus zeta. I'm going to add this measure here, which is this coupling. No, I'm not doing what I want. So I want to put there a measure that when I project here compensates for what I removed, right? So when zeta will give me eta restricted to b, but that's not what I removed. I removed pi 1 star of c restricted to b times b. That's what I removed. And the other one is pi 2 star of c restricted to d times d. Okay? So so if I project this, it gives me eta when I project, right? This gives me minus pi star 1 of C0 b times b, and then plus what? Plus the projection of zeta, which is precisely pi star 1 of C0 b times b.
How do you count for measures on different spaces?
I can think of them as measures on the space that vanish outside of that domain. The restriction, when I have a measure mu, and I write restriction to d, this is in M. This is still in M, but it's defined as the restriction applied to some set is just mu of d intersected with the set. So it's in the same space. However, there is one problem with that, and that is that I can only couple measures that have the same mass. So I have to look at these. This is not yet entirely correct. I have to look at these and try to understand how these masses are related. Okay? Now, so let's do that. And we have a certain number of relations. Well, this is not done yet, okay? What I observed here is that if I do this, the C1 that I get projects nicely on the first coordinates, but it's not symmetric. To make it symmetric, I will have to put something here to compensate. So we are not done yet. But it's time to do some calculations. And let's look at this. So property 1. If I take C0 of C times C plus C0 of C times D, so what does this mean? It means this square here, and then this rectangle. Okay? This is the same thing as C0 of C times P, and then since C0 projects to eta, this is the same thing as eta of C. Okay? Analogously, C0 of D times C plus C0 of D times D is C0 of P times C. Now I'm summing this square and this rectangle, and using the fact that C0 projects in eta, this is equal to eta of C. Okay. Sorry, I didn't write it properly. This is d times p. And this is eta of d. Okay. Now, the other property is that C0 of C times D is equal to C0 of D times C, because the measure C0 is symmetric. Okay? So you look at the first two equalities. You have the same term here and here. The sums are different. Eta of C is smaller than eta of D. This is C, and this is D. So this is bigger, and these two are equal. So the conclusion is that C0 of C times C is smaller than C0 of D times D. Okay? So this assumption about less than 1/2 means that the mass that you have here is smaller than the mass that you have here. Okay? And that's why I drew this rectangle, this square very big and this one very small. So, let's call theta, I think I call it theta, the quotient. Of course, this is bigger or equal. This is bigger or equal than C0 of B times B. And now I'm going to call theta the quotient. Okay? B is an even smaller box here. So that relation there, remember that the projection preserves the mass. So theta is also the quotient of this mass by this one. So to make sure that they have the same mass, I'm going to write here theta. And now it's okay. I just multiply this measure by theta. Okay? The fact that theta is smaller than 1 will have to be crucial at some point. Okay, but not yet. So this is the kind of game you can play with couplings. I want to remove the mass completely from here. I do that. Then it doesn't quite project the way it should, so I compensate by putting some mass here, carefully. And now, the way it is, it projects very nicely on the first coordinate. But of course, it doesn't project on the second coordinate, and it's not symmetric. There are two problems in the second coordinate. One is that there's mass missing here, and there's too much mass there. Okay? But before I do that, let me observe that that the region where I'm putting this mass is B here in this coordinate, and D there. In particular, this corner here, which is the point closest to the diagonal, is far away from the diagonal. Okay? So this part of the mass that I'm adding there will give some contribution to the energy, but that contribution is going to be bounded. Because when I write the integral with respect to C1, it will be a sum of integrals with respect to different measures. And the integral with respect to zeta is not a problem at all, because zeta is far away from the diagonal. Okay? By the way, that's the reason why I need two balls, the ball of radius rho and the ball of radius 2 rho, to make this go far from the diagonal. But we are not done yet. I have to make this coupling symmetric, and I do that very easily by doing the same thing here, by bringing this measure here as well. And I can save my time by saying that I'm just putting here I star of zeta, so plus I star of zeta, where I, or J star of zeta, J is just the reflection. J is the map that exchanges the roles of x and y. Okay? Good. So what? So now I have a measure that is symmetric, but unfortunately it doesn't project to eta anymore, because well, I needed this to make the projection, the second coordinates, be fine here. But if I look at the projection, so for example, projection in the first coordinate, is it okay? I remove this, I compensated with that, but now I had to add this. So it's wrong again. So I have to subtract. Okay? I have to subtract. I have to subtract in such a way that this mass is again compensated. Now, what is the projection of this in the first coordinate? Or in other words, what is the projection of this in the second coordinate? It's theta pi 2 star is this. Okay? Zeta, I didn't explain to you why I'm doing that. I chose that factor. Zeta, when I project it in the first coordinate, gives me pi 2 theta times pi 2 star, etc., etc. So this reflection, when I project the first coordinate, gives me that. So how do I compensate for that? Easy. I subtract theta times C0 restricted to D times D. And now I sincerely hope that it's okay. But let's check. Let's check. What is the projection of C0? Of C1? It's eta minus pi 1 star of C0 restricted to B times B plus pi 1 star of C0 B times B plus the projection of this, which is theta pi 2 star of C0 D times D, right? Here, When I project this in the first coordinate, it's the same thing as projecting that in the second coordinate, which gives this. And then minus theta pi 1 star of C0 d times d. Okay? And then this cancels out with this, and this cancels out with this. Well, you probably noticed that there's a 1 here and a 2 there, which means, well, the measure is symmetric, so it doesn't matter, but it would probably have been more clever to write here a 1. And then there will be no confusion. But it doesn't matter, it's symmetric. C0 is symmetric, and the domain d times d is symmetric, so the two projections are the same. Okay? So this is a game that you learn to play. You can remove mass from here, but to compensate, you have to put it somewhere else. And when you do that, you have to compensate elsewhere as well. Okay? Now the big question, where did I use the fact that theta is less than 1? I want this measure to be positive, or non-negative. I don't have the right to remove more mass than there is. And here, I'm removing the mass of C0 on this pink square. But fortunately, I'm only removing a fraction of it. I'm only removing theta times that. Okay? If theta was bigger than 1, then this would be a measure with sign. And that I cannot do. Okay? So crucial here that theta is smaller than 1. And that's where the 1/2 enters into the picture. You can remove mass as long as you have where to dump it. And for that you need more mass outside than the one that you are removing. And that's why we have this 1/2 condition. Okay? So what did I succeed in doing here? I succeeded in removing mass from the neighborhood of this point. So my new coupling, so I have, summary is, I have a new coupling. So C1 satisfies that C1 restricted to the ball x row times x row is 0, is identically 0. And C1 is less or equal than C0 plus zeta plus j star of zeta. It's smaller because I removed this and I also subtract this, but I don't really care. The point is that these two are supported far from the diagonal. I cleaned up this little square here, and I put the garbage outside of the, far from the diagonal. Okay? So how do we finish the proof? So to finish the proof, finish the proof, we consider a finite set x1, xl in P such that the balls of center on these points cover P, the compact metric space, and you do this construction, the same construction L times so I just explained how to do it once, but to go from C0 to C1 using the point x1. Then you do the same thing with the point x2 and you get xc2 and so on. After L steps, you get a coupling. So after L steps, we get coupling CL. So we get coupling, symmetric self-coupling. CL that has the following property, such that CL is restricted to some neighborhood of the diagonal is identically 0. You go removing the mass from these little squares, being careful not to put the garbage close to the diagonal, otherwise the second time you could be ruining what you did the first time, but you don't do that. Okay? So in the end you get a coupling such that there is some neighborhood of the diagonal and the coupling is 0 here. Okay? As we also observed last time, that implies that the energy of CL is 0, is finite. and so the energy of your measure is finite. Okay? It's just you have a compact set. You have a compact metric space. You just take the cover by balls, and there's a finite cover. It's just a number of elements of that finite cover. Okay? So this argument says quite a lot about what we can do with couplings, and a little bit of what the name of the game is when you deal with these guys. Okay. So now let's try to finish the proof of. This is a never-ending proof. We get various kinds of contradictions, and we are always ending the proof. But let's move forward. So. So, proof of the theorem. I'm going to suppose that this is an atom. So suppose this is positive. Then we can find a neighborhood. We can find a neighborhood U0, neighborhood, such that the measure of this atom is bigger than 9/10 of the measure of the neighborhood. I'm going to fix a neighborhood like this. Now remember that I'm assuming that the point is expanding. Being expanding means that on average the distance tends to increase. As I apply my matrices, the distance, this is like a source, like a repeller. On average, distances here tend to increase. And so, since the energy is defined as the integral of 1 over the distance, the distance should tend to, the energy should decrease. And that's the secret. Well, we will have to work to make the secret function, but the secret is that because of the expanding behavior of V, the dynamics tend to relax the energy, tends to reduce the energy. So, in the end, we are going to prove that the energies of the eta k are uniformly bounded. So when you go to the limit, the energy of eta is finite, and if it's finite, it cannot have an atom. That's how it goes. That's why energy and atoms talk to each other. But we need a first lemma. We want to use the assumption that V is mixing, is expanding. And we have this lemma saying that if delta is small enough, then and n is large enough, then the integral of derivative a n x v v dot to minus delta d mu of x is smaller than 1. The c is the same c that appeared in the definition of expanding. Expanding meant that the integral of log d a x b v dot d mu x is bigger than c. And in fact, to be correct, I have to put a 2c here. Sure. It's not exactly the same c. This is 1/2 of that one. Okay? for every unit vector. Okay, this is the kind of lemma that it's easy to believe, but requires a proof. But I want first to give you the chance to believe that there's something to do, that has something to do with this. So what are we doing here? What does the definition mean? It means that on average, the logarithm of this derivative is positive. On average, the logarithm is positive. That means that in some sense, on average, the derivative is bigger than 1. Right? And if the derivative is bigger than 1, then you expect the derivative to some power minus delta to be smaller than 1. And so you expect the average to be smaller than 1. Okay? So the two inequalities make sense together. This one is saying that the logarithm is positive, and this, in some sense, is saying that 1 over the derivative is bigger than 1. So it goes the right way. But the proof actually requires a little argument. I was a bit surprised. And this is an argument that is well known to analysts. A very elementary, very useful argument that I'm going to present. So what you do is that you consider the function c of delta equal integral of dan x v dot d mu x. Okay. This is a function, I see it as a function of delta. It also depends on other things. For example, it depends on v dot. I think that's all it depends. Well, it depends on n also. But that's not so important. So that's a function, because you see, the moral argument that I gave you, logarithm bigger than positive, is related to having 1 over the norm over the function smaller than 1. It's only a moral argument because I need delta to be small for this lemma. But it has to be a little bit more subtle than what I said. So let's look at this as a function of delta. And observe that c of 0, if I write delta equals 0, this is just 1. And I'm integrating with respect to a probability, so this is 1. And then the trick is to take the derivative with respect to delta. Derivative with respect to delta is, well, you have to go back to the laws of derivation, is the function the minus delta, and then the logarithm. And I think there's a minus sign here. It's a minus delta. Okay? So you see, c prime 0 is the integral, is minus integral of the logarithm. Right? And so it is smaller than minus 2c. So now the rest is easy. You have a function which is 1 at 0 and whose derivative at 0 is less than 2c, minus 2c. So it's decreasing. So it has to be something like this. This is 1. So the conclusion is that c of delta is smaller than 1 minus c delta for delta small. Because it is 0, it is 1 at the point 0, and the derivative is smaller than minus 2c. Okay? Then you have to pay attention to the fact that this is a function on delta, but we also have n and v dots. So you should write n and v dots all over. And it's done in the book. All estimates are uniform. In V dots and n. So that you have this statement here. And n for n large. So that you have this statement as it is with the right quantifiers. Okay? You have to check that you have uniformity, but you do. And so we have this property here. Okay? So what did I do here? I had this definition of expanding, and I transformed it into another form which is more appropriate for proving what I said, that because V is expanding, the distances tend to increase, and so the energy tends to decrease. So here is how I formalize that. So take a neighborhood U1 contained in U0, a neighborhood of V, such that take a neighborhood U1 such that for any V1 and V2 in this neighborhood, when you calculate this integral, you get less than this. Now, how can you do that? You have the point V. You have this big neighborhood U0 that you already fixed. And now suppose that you have 2 points that are very close by. I'm going to remove the brackets. I'm getting tired of these brackets. V1 and V2. Okay. What happens to the distance between these 2 points when I apply one matrix AX? Well, the point V remains fixed. V1 goes to AX. I'm going to apply n times. ANX V1. This goes to ANX V2. And the new distance is the old distance times, I'm using the mean value theorem. Mean value theorem tells me that this distance is this distance multiplied by the derivative on some point in between. So times the derivative where V3 is some point here in between. It's by the mean value theorem. Okay? This looks complicated, but it's not. I can take this out. This comes out. So I get 1 over distance xy to the power delta. And then I have the integral of what is inside. But if I take a neighborhood which is sufficiently small, I don't know where V3 is, but it's certainly close to V. Okay, so I can pretend that V3 is similar to V. So I get 1 over the norm. And this is smaller than 1 minus C delta. Any questions? Oh, that was nasty. This is V1 and V2. Sorry, I drew the picture correctly, but this is V1 and V2. Sorry, this is completely incomprehensible the way I changed. Okay? I'm just saying, when I apply a matrix A, well, A iterated n times, then something happens to the distance between the points. What happens to the distance is determined by the derivative because of the mean value theorem. And the derivative on average is bigger than 1. So on average, this distance will be strictly smaller than the original distance. Okay? I'm exploring the fact that the point, the center, is a repeller. And the neighborhood U1 is just taken so that this approximation is correct, that taking the derivative on this unknown point in between is essentially the same as taking the derivative on the center point. Okay? So why is this nice? It is nice because of the following fact. Let us draw. So I'm going to pretend that the point is here. This is my product, P times P. And here is U1. U1 times U1. So let us yeah. I'm sorry, this was not correct. This was not correct. Let eta k be nu k stationary and non-atomic. I mean, it doesn't change anything that I said. Not here. Yeah. It's not the new case that I'm worried about. It's the eta case. Non-atomic. Okay. I mean, it doesn't change anything I said, but that's the correct statement. And here it's going to be important. So for each k, take any self-coupling ck of eta k restricted to u1. I only want to consider the behavior of take any self-coupling ck of eta k. I'm considering the behavior near u1, that's in this neighborhood, with finite energy. Okay, so why can I do that? By assumption, eta k doesn't have any atoms. In particular, it doesn't have atoms in this neighborhood of V. The measures eta k. The one that I want to prove, the one I'm assuming has an atom is the limit. I'm going to say if I assume that the eta k's don't have atoms in the neighborhood, then the energy is finite. Because, okay, so take any self-coupling, ck, and then the important step is to consider the image of this coupling by what we call the diagonal push forward. The diagonal push forward. The diagonal push forward is the map associating to each V1 and V2 the pair AX and V1 AXN of V2. So C is a measure here. And I'm going to consider the image that I'm going to call C twiddle K, the image of this measure under the diagonal push forward. So what this means is that, for example, that CK, well, that the integral of any function with respect to CK, that's what I mean by diagonal push forward, is the integral of psi ANX V1 ANX V2. You integrate with respect to CK, and then you integrate with respect to X for any bounded measurable function C. And look at the nice thing. The energy of CK twiddle is the integral of 1 over distance V1, V2 delta of right. And then according to this formula, it's the distance, it's the integral of ANX V1 ANX V2 d CK X v1, v2, d mu x. But then this integral that appears there is less than, where did I write it? Is less than 1 minus c delta 1 over distance from v1 to v2 to the power delta. So this is less than 1 minus c delta 1 over distance v1, v2 to the power delta, integrated with respect to c. And this is 1 minus c delta, the energy of ck. I really don't know how to go around the formalism. I have to write some calculations, but the geometry behind these calculations is much more transparent than the formulas. Near V, on average, my map expands, takes electrons and puts them further away. So if I take a certain mass distribution of electrons here, and I do the push forward, the diagonal push forward, this will tend to move particles further away, and so it should decrease the energy. And here it is. The energy of the push forward is less than some small factor, smaller than 1, times the energy of ck. So what I would like to do next would be to say, take eta k, choose some self-coupling with finite energy. Use the dynamics to construct another self-coupling with smaller energy. But this is not going to work. There's something that's not correct. But suppose you could do that. This would be a machine to construct for eta k self-couplings with small energy. Maybe the one you started with in the beginning had large energy, but use the dynamics to reduce the energy. And in this way, you hope to prove, and that's what I want, we want to prove, this is the proposition that I'm aiming at. There exists C such that the energy of eta k restricted to U1 is less than C for every k. This is what I want. I'm assuming that the eta k's are non-atomic, so they have finite energy. That's fine, but that doesn't mean that the energy is uniformly bounded. However, it seems that I have here a little machine called dynamics to start with one self-coupling and produce another one whose energy is smaller. So even if the first one is very bad, I apply this machine several times, I decrease the energy, and I hope to prove this proposition. The proposition is correct, but the proof is not yet ready. Okay? So once I get here, let's see how we finish. Okay? Suppose I prove this proposition. Suppose I prove that the energy of these stationary measures is uniformly bounded on a neighborhood. Okay? Now, eta k converges to eta. Right? And so, the energy of eta is less or equal than the lim inf of the energies of the eta k's. Why is this? Because that I didn't say. There's another property, lemma, or exercise. The function that to each eta associates its energy is also lower semi-continuous. I stated the corresponding result for, at the beginning of today, for measures in products in P times P. But this is also a lower semi-continuous. So if E delta eta k restricted to U1 is smaller than constant for every k, then by lower semi-continuity, E delta eta U1 is less than that constant when you go to the limits. Okay? But this is finite. So eta has no atoms. So eta has no atoms with mass bigger than 1/2 the total mass of U1. No atoms in U1 with total mass bigger than 1/2. And somewhere we chose these neighborhoods U1 contained in U0 in such a way that eta V would be bigger than 9/10 of the mass of U0. So this is in contradiction. I assume that V is an atom, and then I find a neighborhood such that V is 9/10 of the mass of that neighborhood, and then through this other argument, by proving that the energies of the eta k's are uniformly bounded, I conclude that the energy of eta is uniformly bounded, and so it cannot have a mass, an atom with mass more than 50%. So there's a contradiction here, and that's how we get the conclusion. Okay. Now, let's summarize. I want to maybe close here for today, and then we'll finish on Thursday. We want to prove that uniform bound for the energy. How do you prove that? For the energy of these stationary measures near U1. How do you do that? You start with a self-coupling, any self-coupling with finite energy, because you are assuming that these eta k's have no atoms, and so they have finite energy. And then this, the property, the assumption that the point V is expanding, allows you to prove that as you iterate by this diagonal push forward, the energy actually decreases. And geometrically, that's very to be expected. Okay? So you can start with any, you could start with any self-coupling, just with finite energy, and reduce this energy so that it becomes less than C. Of course, you cannot do that, because if you could do it the way I'm explaining here, every time you'll be multiplying the energy by a factor less than 1, so you would be proving that eta has 0 energy, and that's not true. Okay? So what is the trick? What's wrong? What is incomplete in the argument? What is incomplete is that when you start with a self-coupling of eta k restricted to U1, and you apply the push forward, what you get is not a measure in U1. What you get is not a self-coupling of eta k restricted to U1. Okay? So we will have to fix this eta k twiddle, to change it a little bit, to make it a self-coupling of eta k U1, so that we can repeat the argument over and over again. Okay? So I will do that on Thursday. I think we already did enough calculations for today. Questions? Okay, if there are no questions, see you on Thursday.